Okay, here we're going to learn how to find the prime factorization of a number. The prime factorization, that sounds like a scary phrase, but it's really just breaking a number down as much as you possibly can into all of its prime factors, all of its smallest possible factors. And factors are really just numbers that multiply to give you another number. So like 5 times 6, those two numbers multiply to give you 30. They're factors of 30. Something is a prime number when it can no longer be broken down into any more factors. It's prime when it doesn't have any other factors besides itself and 1. So we're going to circle all the prime numbers here. 2 is a prime number. 2 cannot be broken down into anything else. Nothing else will multiply. No other whole numbers will multiply to give you 2 besides 2 and its 7 is the exact same thing. There's nothing that multiplies to give you 7 except for 7 and 1. 6 is different. That breaks down into 2 and 3. 2 and 3 are both prime, so that's as far as we can go with that little factor tree. It's basically just breaking it down into what multiplies to give you that, but that tree can't go any farther because 2 and 3 are both primes. 9 can also be broken down. So that's not a prime number. That can break down into 3 and 3. Even though it's the same thing twice, it's still not a prime number because it's a composite of those two primes. Negative numbers are all composites. Composites are the opposite of primes. It basically means it can be broken down because they have a factor of -1 in it. So -1 times 2 would give you -2. So that's two separate factors for -2. You could try dividing 151 by a bunch of different numbers. You know it's not going to get divided by 2 because it's not even. So you can try 3, 5, 7, 11, 13, 17, some of the bigger odd numbers there. But nothing is actually going to divide 151. That does not break down at all. That's a prime number. 51 seems like it might be prime also, but if you try 3, 5, 7, actually you hit one with 3. 3 times 17 would give you 51. However, 17 doesn't break down anymore, so 17 is actually a prime number. 91 also seems like it might be prime, but if you try 3, 5, 7, 11, 13, actually 7 and 13 break down 91 also, so that's not prime. 106 is an even number, so we know that's not prime. And 1,833 seems like it also might be prime, but if you test out some numbers, that gets divided by 3. 3 times 611 would divide that. And actually, you can tell right away if something's going to be divided by 3 if its digits add up to a number that's divisible by 3. You don't have to know that off the top of your head. You can just test to see if it's divisible by 3. But you can also see 1 plus 8 plus 3 plus 3. When you add up those digits, that gives you 15. And 15 can be divided by 3. So this number can also be divided by 3. That's just one of the weird things that happens with the digits of a number that's divisible by 3. So what we just showed was factoring some numbers. The prime factorization is just taking that an extra step, factoring until you can't factor anymore. It's breaking down a number into a multiplication problem between all of its prime factors. Factor until you can't factor anymore. You can factor it however you want. So 20, on that first example, it can break down into a 4 and a 5, or into a 2 and a 10. Eventually, you'll get down to the same exact prime numbers. It actually doesn't matter how you do it. I'm going to choose 4 and 5. 5 doesn't break down anymore. I'm going to circle them. When you get down to the end of one of these, I'm going to call that a factor tree, end of one of these limbs of the factor tree, circle them. I know 4 can break down. Now 4 can break down into 2 and another 2. 2 cannot be broken down, so I'm done with that end of the factor tree. Those are all of my prime factors. And I'm going to write that as a multiplication problem. I'm going to write that out as 2 times 5. All of these multiplied together would give us 20. I'm just showing 20 broken down into its 3 factors, which are 2, 2, and 5. Same exact thing on the next one. I'm going to try to break down as much as possible. I see it's an even number, so I know 2 will divide it, but I also know some bigger numbers that will divide that, like 6 and 8. 6 is not prime. I can break that down into 3 and 2. 8 is not prime. I can break that down into 4 and 2. So I have a 3, a 2, and another 2. Those are prime, so I'm going to circle those. But I have a 4 that can also be broken down a little bit into a 2 and 2. 2s, 3s, 5s are generally where you're going to end up. Sometimes you'll end up with 7, 11, 13, 17. Smaller primes. Generally, these are not going to break down into bigger numbers. That's not always true, but generally you're going to get down to smaller primes. That is our list. We have 4 2s. And we have a 3. You can test to make sure that you did this correctly by just multiplying them back together. 2 times 2 times 2 times 2 times 3 should give you 48. Same kind of thing in number 3. I'm going to take out the 100 right away. I'm going to take out 2 and 100. 100 is going to break down into, we have some options there. Let's do 4 and 25. And then 4 breaks down into 2 and 2. And 5 can break down into 5 and 5. And that's our list of primes. We have 3 2s and 2 5s. So you can write that out as a long multiplication problem like that. Sometimes you also might see an exponent on the 2 or on the 5. So since we have 3 2s, instead of writing that as multiplication, I can write it with an exponent. 2 raised to the 3rd power. Instead of writing 2 5s, I can write 5 raised to the 2nd power because I have 2 5s being multiplied by themselves. $201 seems like it might be prime, but if you test the numbers, you see that 3 breaks it down. 3 times 67 will give us 201. You can try any numbers, any whole numbers you want, but 67 doesn't break down anymore. Try dividing by 3, 5, 7, 11, 13, 17. That's your list of options. If you get stuck, those 6 options should be what you try, and maybe even a little bit more, but nothing is really going to break down 67. When you have a negative number, the first thing I want you to do is factor out that -1. We know that that's one of the factors. Then I'm going to factor in 94 just like normal, so I'm going to break that down. I see the 2 can factor out right away because it's even. And 2 times 47 would give me that 94. Nothing is going to break down 47, so that is my list of primes. It's -1 times 2 times 47. Last one, 81 gets divided by, let's do 9. Divided by 9 and divided by 9. But 9 can be broken down a little bit more into 3 and 3. So we have 4 3s there that are getting multiplied. You can write it either way, as 3 times 3 times 3 times 3, or just 3 to the 4th power. Either way is okay. you should be able to do the rest of these on your own. Show each of them as a multiplication problem in the box at the bottom of each problem, but also show the factor tray. I just want you getting practice with this because we're actually going to take this a step further in our next lesson.